Now we start with the Feynmanian part. Mainly we want to take action functional and try to figure out whether it can be renormalized so that you can get conformal field theory. And then the first question is what sort of action functional would be a good guess to start with. And of course it should, one criterion maybe should be that maybe it should be classically conformal, right? Okay, so, and I talked about conformal invariance in terms of in terms of plane and Möbius maps, so actually Riemann sphere and Möbius maps. But in this action functional business, it's, remember you were talking about local functionals of the fields and integrals over the space of that. And in physics again, or in mathematics also, there's a very natural setup to talk about conformal invariance from in that setup from the sort of not in terms of conformal maps, but in terms of Riemannian geometry, and so you start with the following sort of setup. Okay, so first of all, your space-time, or the Euclidean space. Now it's two-dimensional surface and smooth two-dimensional surface, equipped with the Riemannian metric G. Okay, so Riemannian metric. I hope everybody knows this Riemannian metric. Now, what are the scale transforms? I was saying that you generalize the scale invariance to spatially dependent scaling. So in this setup, it's very natural. You just multiply your metric by arbitrary function, positive function. So that means that the metric tells you how infinitesimal tangent vectors, what are their inner products. And then if you multiply your metric by a positive function, then the angles don't change, but of course the lengths change. Okay? So we say that two such metrics are conformally equivalent if they are just multiples of each other by a positive function, which positive function you could write as exponential of some smooth function on the surface. Okay? Okay, so then the local action function in this setup then is the following. You have some density, this L here, Lagrangian as it's called. And it should be a local function, not of the field and of the metric, okay? And you want it to be, you say that it's conformally invariant. First of all, you can make changes of coordinates or act with diffeomorphisms. So if you compose the field by a diffeomorphism of the surface, and at the same time move the metric, I denote it by psi star G, so this is how metric changes under diffeomorphisms. Then it should be invariant. Okay? That's sort of going back to Einstein idea. And then the conformal invariance comes here. It should be also invariant when you multiply the metric by this function. Okay? This is usually called wild invariance. Let's look at some concrete examples. It's better. Okay? So let's look at our free field again. So the manifold. So remember the field was here. The values were. It was defined on the two-dimensional surface, and it took values in some space, which we take manifold, and the simplest example is free field, where it's just takes values in real numbers. And then you just take the Dirichlet energy. So what is it? If you write it in nice notation, you take the differential of the field and take its length at a point. Length, the Riemannian metric on tangent vectors, it gives also a metric on cotangent vectors, so you can take the square. And if you write it in terms of coordinates, the metric, Riemannian metric, it's this tensor. Every time I have one index repeated, it means that it's summed over. I'm using the Einstein convention here. So Riemannian metric is determined by this in two dimensions. It's spatially dependent positive 2 by 2 matrix. And the inverse of that matrix is the metric in the cotangent vectors. This is the metric in the tangent vectors. And in that notation, it's just take the derivative of the function and contract the indices with this inverse metric, and that's the Lagrangian. Okay? And this is explicitly invariant under diffeomorphisms because everything is written completely covariantly. But it's also invariant under Weyl transformations. Namely, if I multiply the metric by positive function, the inverse guy is multiplied by the inverse of that function. And if I integrate over the surface with the volume, the volume form, the Riemannian metric is square root of the determinant of this matrix. Then you get e to the plus sigma from one and to the minus from the other, so it's also one. It's of course just a dish, the energy, and it's a natural mathematical object. Its critical points, the Euler-Lagrange equations, are just harmonic functions of the manifold. So that is any question about that, about notation, because we are going to use, unfortunately, a lot of the notation of Riemannian geometry now. You can generalize it, make a more nonlinear thing about that. It's called, in physics, it's called sigma model. So now you take the field, take values in another Riemannian manifold. So the target is also a Riemannian manifold. So I call it capital M, and I call the Riemannian metric little m. Okay? So what is the derivative of the field? Let's think about it abstractly first. It's a cotangent vector on your there's a misprint here. This should be sigma here. Sorry about that. Okay. So it's the differential. So it's a cotangent vector in the on the surface, and it's a tangent vector here. Okay. So there's a natural metric here, a natural metric here, and then with this very compact notation, then the Lagrangian is again the absolute value squared of this derivative. If you write it concretely in terms of this metric, so you choose some coordinates on this target manifold, so call them phi alpha, phi I and phi j. So this is a Riemannian manifold, so it's some n-dimensional space, n-finite, and it's called the coordinates locally phi I, so I is Rn, and then the action function looks like this. So you take derivatives, and this is as we had in the free field, but now we have our indices in the field, and then we have some nonlinearity coming from the Riemannian metric, the target computed at the point phi. So it's such a beast here. So it's like in the free field, but then there is also some extra phi dependent term here. Okay? That's mathematically also a very natural object, just like harmonic functions. These are now called harmonic maps, the solutions of Euler Lagrange equations. But they are highly nonlinear PDEs now, even to study the classical theory here, highly nonlinear PDE to solve. Don't worry if you're a bit lost with what this exactly. We are going to write down very explicit examples. Oh, no. Apparently somebody didn't like the lecture. Okay. In this setup, you might say that, okay, why don't we look at the 5-4 theory, which we previously had. So I was thinking about 5-4, but you could as well put any polynomial on the field phi. And in 2 dimension, these theories were constructed by Graeme and Jaffe and others for any even polynomial. Why don't we think about this in terms of this conformal invariance? Well, it's obviously diffeomorphism invariant, exactly like the free field. But it's not wide invariant because of this P here, because the volume changes by e to the sigma, and there is nothing coming from anywhere else, unlike when you had just something depending on the derivatives. So this is not wide invariant. So we don't expect, well, the classical theory is certainly not conformal. And the same way, if you take sine-Gordon model, where this is cosine of the field, which is Christoph is going to discuss this model, or the so-called Sinch-Gordon, the Koch, they are not wide invariant, so these are not conformally invariant consequently. So these are not very good guys to start with if you want to talk about conformal field theories. Okay? And they are not expected. Question? Okay, so these are not conformally invariant consequently. There's one example, one counter-example to this claim, namely that if you put here some function of 5 only, and that's called the Liouville model. And Evelina told me that you know everything about Liouville models, so I don't have to talk about that. But let me anyway talk about it. So here the target is just R like again, and you take exponential of the field. So this certainly alone would not be wide invariant. But then you do this funny thing that you add also a linear term in the phi. And then this thing is almost wide invariant, provided you choose these parameters. There's a one parameter Q here and another here. The mu plays no role in this, what I'm talking about. So the Q and the gamma are the ones, if you tie them together with this formula here, and the Q is 2 over gamma, then this action function is almost wide invariant. And then if you multiply the metric, this is a good exercise calculation, multiply the metric, then you can undo it, but just by a simple shift in the field. So it's not invariant. The field gets shifted. Modular term which doesn't depend on your field phi. So a constant which depends on the metric and what you put here. And this term is called so-called Weil anomaly. So there's this expression here. So there's a Dirichlet energy of the shift, and then linear term. Again, I'm sorry, I'm using K and R are the same. K and R are the scalar curvature of the metric. We'll come back to that maybe tomorrow. But, it's just a certain geometric invariant. And if you take this action, then it's almost conformally invariant. Yeah. And it turns out to give rise to a conformal field theory also. I think I put here a recollection just what it means to be. I wrote the formula for the curvature here. So if you go, first of all, in this setup, it's Riemannian surface, but it's actually a Riemann surface in the sense that you can choose coordinates on the surface locally so that the metric takes Euclidean form times a function, and then the Riemannian volume is then very simple. It's just this function times the Euclidean volume, and the scalar curvature is just Laplacian acting on the logarithm of the metric factor here. Okay, and the minimizers in this setup, once you write and that's also a useful exercise to do, write down the Euler and Lagrange equations. So I will come back to this tomorrow. So they are just functions phi such that once you multiply your starting metric by exponential of phi, the scalar curvature of the new metric is constant. Okay. This is why it's called nu. It came from uniformization theory and that kind of business. Okay, so here are our examples. We are going to discuss the sigma model tomorrow. But before I go to that, let's continue with a very general discussion. So, what are you supposed to do? Suppose now you decided, okay, now I have this sigma model, for instance, I want to construct it. So I'm supposed to make sense out of path integral, write that, okay? So take exponential of the action function of, I had to figure out what are the natural guys here, okay? And then want to make sense of this path integral. So and what did we learn from phi-4 model? We are supposed to regularize and then maybe renormalize, maybe add some competence or something. Okay, so what happens when you try to do that? The simplest thing of these examples where it was studied is the case when let's be just on the plane. And take the Heisenberg model. Actually, Christoph is going to discuss this model once he arrives. You take just the target manifold, the sphere. Okay? And so S n minus 1. So, and take the round metric of the sphere. It's the usual metric of the sphere. How do I figure out how to renormalize? Well, that answer to that is given by the renormalization group. You try to do this thing where you do the following. You want to see how once you go from scale to scale, what you put here changes. That's basically what you try to do. And this calculation was done by Polyakov in the beginning of 80s. And the answer was the following, namely, if you do the following, you put it on a lattice, for instance, epsilon spacing lattice, and you modify it very simply. You just multiply the metric by a number, epsilon-dependent number. Then if you choose this number in the correct way, then you expect the following. None of this is proven, so this is just a heuristic calculation. You expect that now you compute these effective actions, as they are called, at different scales. Then they are flowing in the following way, namely they just flow with the same number here, but now epsilon changed by L. Plus some terms which are usually called irrelevant, they don't make they are not interesting, let's forget about them. Where this parameter, what you have put there and what describes also what your theory looks at, like at different scales, satisfies this simple equation here. Okay? So, how it depends when you change the scale is given by the n, of the sphere enters here. There's a quadratic term here, and then there are cubic terms. So this tells me this is holes if t is small. Okay. If you solve that equation, what is the solution of this equation if you just take it literally, it says that T of L depends on L like, well, there's n dependence, 1 over n minus 2 times log L inverse. So, in particular, this TL is smaller and smaller as L goes to 0. So you have to put here TL smaller and smaller. And then it's sort of reasonable that this might be, there must be some truth in this calculation, which is supposed to be done for small t. This is called asymptotic freedom, namely if you now look what it means, this action function of your rescale a little bit with the t, you see that you are going to the free field when L goes to 0. Okay? Or if you interpret it in terms of statistical mechanics, this is the temperature, so you're going to the 0 temperature. Okay? This analysis is supposed to be valid for small t.
Is there a reason because if you take the sphere and you take this metric, make the sphere larger and larger, and then
Exactly.
you don't see that you're in a sphere anymore.
Exactly. Exactly.
So what is this metric?
Exactly. That's what happens.
Or can
So the
or
nonlinearity is.
can or manifold the Ricci flow.
Yeah, so that comes here. So, but anyway, this shows that if you succeed showing that actually that's what is true, then it's not going to be a conformal field theory because things depend on scale. Okay. So for L going to 0, it goes to the ultraviolet fixed point, which is the free field. For L going to infinity, it's believed to flow to high temperature fixed point, namely this temperature parameter goes to infinity. And this has exponential decay believed to have, well, if it did that, it's known to have exponential decay and correlations. And to prove that, this theory has always exponential decay and correlations is, of course, one of the big open questions in mathematical physics, which is still open, comparable to the confinement problem we talked about in the morning. Okay, so here are the maybe not billion-dollar problems, but maybe fields-medal problems, I suppose. Actually, for n equal to 2, that's the only counterexample. You see, then this thing is 0 here, right? That's when the sphere is just a circle. And then you actually have a conformal field theory. It's called the free field, taking compactified free field, namely the target space is circle, otherwise it's sort of Gaussian free field. And that's a conformal field theory, a simple conformal field theory. Okay, and then as Hao was saying, then if you take a general signal model, there's a classic calculation by Friedan in the beginning of the 80s, where he showed that the same picture holds, the similar picture holds, namely, in more generality, namely, now the effective action, you start with some metric, the effective action, once you do this, flows with scale. The renormalization group equation is the Ricci flow equation, plus irrelevant other terms, where Ricci tensor is, well, from Wikipedia if you don't know it, it's a particular tensor, and that's how the renormalization group equation flows. Okay, so this says that fixed, but if you want to have sort of conformal field theory, this should be 0, right? Like here, or equal to 2. And so that makes you sort of believe that if your target manifold is Ricci flat, then you might have a chance to produce a conformal field theory, because at least in the leading order it doesn't seem to change. Unfortunately, that's not to be really true. The higher order corrections spoil this. And there are some examples where you might have some chance of getting a conformal field theory, but not really. So there are cases where you can compute this sort of order by order, and this small parameter, this equation, the flow equation, and all the terms seem to be zero, so then in that case you might expect that there could be a conformal field theory there. However, who told you that those are all the only terms you can put into the action function, no? There's another term which is, it was important to have second derivatives, two derivatives in the action function, because that's e to the sigma and e to the minus sigma cancel each other. But you could take a 2 form into the target manifold. Then suppose there is some 2 form in the target manifold. Then there's a natural action function. You just take the derivatives and contract it to this 2 form. And this is not only conformally invariant, but this is topological. It doesn't depend on the Riemannian structure at all. It's just it's usually called topological term. And there is a model called the WZW model, which we're going to describe tomorrow, where taking such a term, you actually expect to get a conformal field. And in some cases, we actually prove that. That's the end of that story. Okay? So the sort of renormalization group analysis, which is, lets you sort of expect that in the end you come up with some examples, and that's what we're going to discuss tomorrow. So let's now formalize what it means to be locally conformally invariant. I was talking about conformal invariance in terms of Möbius maps, but let's formalize now. So what you would like to prove if you have this, you construct this path integral. What set of things you would like to prove? Okay. Okay. So in the Riemannian setup, so now the axioms should be that I told you what it's classical. The action should be diffeomorphism invariant and wide invariant. So here we are talking about correlation functions. So suppose you construct them, and they depend on the metric. So we still want them to be invariant under diffeomorphisms. Maybe if we move the points and the metric, nothing should happen. Okay? But it turns out that, like in the Liouville, which I told you, that was not classically conformally invariant. The wide invariance, there was this anomaly. Turns out that you can't expect to have wide invariance, but you have almost wide invariance, namely, want to multiply the metric by a positive function, then you get this prefactor you wanted to have. This was what we had in the Möbius also. But then there is some mysterious factor, this anomaly, namely, there's an exponential of this function of what you multiply and the metric, and so this anomaly function, times some number which is called the central charge of the conformal field theory. That number here depends on what actually is your conformal field theory. So that's what local conformal, that's what conformal invariance in this Riemannian setup says. If I now compare to what we had before we had the Riemann sphere, so sigma was complex plane with a point at infinity. Psi was a Möbius map. So then if you compute what is the pullback of the metric, then it's just the derivative of the psi squared times the metric composed with the psi. And then if you plug it in here, and that's again a calculation which you should do. If you plug it into this anomaly here, it actually vanishes. So this is the same axiom as we had on the Möbius. Okay? The anomaly vanishes, and we have exactly psi prime to power delta and what we had before. Okay, so that's what we would like to do. Questions? I want to see now what are the consequences if we have this. Okay, that's the last topic I want to describe. This is sort of the end of the 60 minutes. Yeah, that was a Freudian slip. Stress energy tensor. Okay. Let's look at the following, okay? So this is a classical, stress energy tensor is a classical object also. So you have this classical action functional, and you could just ask how does it really, what is it dependent on how does it vary when you change locally the metric? So let's look at the variational derivative of the action functional when you vary the metric at point x. Okay? So by that I mean the following. So it's more convenient actually to look at this variation not for the metric but the inverse matrix. So remember I used the upper indices for the inverse matrix. That's a sort of physics convenient. So let's take your metric, inverse metric, and add a small parameters, a smooth function so that they are still positive. And then compute the derivative at epsilon equal to 0 of the action functional. Then obviously what you get is a linear functional in the thing what you add, because it's a derivative. And you can write it in terms of as an integral over the volume times something. Okay, and that something is called the stress energy tensor. It has to be contracted with this f which we add, so it has to have two indices, and it will be a local function because our action was local. And if you do it for the free field, that's the answer. Okay. That's an exercise, actually. The second term comes because you have to remember that you're also varying the volume. Okay. And then an even more interesting exercise is to compute for Liouville. And if you start doing the calculation, you're soon getting crazy because there's the Ricci curvature, and during that you have to go to Christoffel symbols and all of that, and when the dust settles, and if you look at Wikipedia for the answer, you eventually are able to complete it, okay? And that's, but I'm not giving you the result here. Okay, but let's see now how would that be in the quantum or in our quantum field theory case. So that was a classical story. We had explicit action functional. Nothing there is very deep, okay? It was explicit action functional and the stress energy is some functional of the field, local functional of the fields. But here we are interested in these correlation functions. So now we ask the same question. Suppose you have a conformal, you sort of magically succeeded verifying the diff and while axioms for your beloved conformal field theory. And now you want to ask what is the stress, okay? So again, do the same thing. Let us vary the metric. So you have constructed these correlation functions. They satisfy our axioms. And do again the same thing. Add to the inverse metric a smooth, compact support thing. Let's make it compactly supported in the complement of these points. We know that we are having some singularities at these points, so let's not do anything there, okay? Let's do it outside of these points. And try to do the same thing. Maybe compute the derivative at 0 of the correlation function in this variation of the metric. And like in the classical case, it should be a linear function of this guy here, times something and that something, let's give it the following name, namely, that something is that we have again this correlation function, but something was inserted at the point z, what you are integrating over. And that's something that we would call the stress. Okay. Okay, so let's try to do that. And the thing which I want to convey to you, and I'm doing this here now because I want to construct what happens with the Kac-Moody symmetry tomorrow. There's a similar calculation there. So, let's make the following assumption. Let's assume that you have proven that the correlation functions are smooth in the region where of non-coinciding points and satisfy the diff and wide invariance axioms. So this, for instance, holds now for Liouville theory, which I didn't define to you really, but everyone tells you that. And then see what are the consequences. Okay, so then, first of all, this function here. Let's work on the sphere. Okay? Then this thing actually is smooth in epsilon, around epsilon equals to 0, and its derivative of epsilon equals to 0 is indeed a distribution, and you integrate over this thing times another function which depends on the points and z, which is also smooth in the complement of the points. So that's the theorem. And then we denote this guy by this, okay? The idea of the proof is very simple. So this is the following. On the sphere, there's only one conformal class. So I will work in the different. Let's work in the class where the metric just looks like this. Let's work in the coordinates where the metric looks like this. And now let's do the variation there. So if you do while and diffeomorphism, we know that there's only one conformal class. So if I start at G, and now I perturb the metric, then that's going to be given, again, it's in the same conformal class, so there exists a diffeomorphism depending on epsilon and a Y transformation, such that that's given in terms of those acting on the static metric. Okay. Well, if that's the case, then the derivative at 0 is just the differential of, you know exactly how the correlation, that was our axiom, how they depend on the while and the diffeomorphism, namely, there's the anomaly, there's the conformal weights, and then there's a diffeomorphism acting on the points. So we are supposed to take derivative of that at epsilon equals to 0. So we get something from here, this is something from here, sigma epsilon, and then something from here, which is clearly going to be a differential operator acting on this correlation function. Okay? So if there is anything, then the result is going to be a differential operator acting on the correlation function. And it's a linear differential. To actually find them, you can do it explicitly. And that's complex analysis. I'm not going to go to that. Okay? You have to solve a Beltrami equation to do that, and in the end, let me just say that solving Beltrami equation, in the end of the day, you have to talk about Cauchy transforms and Beltrami transforms and functions like 1 over z enter the story. there's an explicit way to do it. If you are interested, look at book by Astala Ivanec and or if you want to see how this theorem is proven, look at the paper by Joona Oikarinen and myself years ago. Okay, but let me just tell you what is the answer. Okay, I'm telling you that this is standard complex analysis. Okay, and the answer is the following. First of all, it's convenient to use the complex coordinates. So instead of using two-dimensional real coordinates where mu and nu run from 1 to 2, x1 and x2, you write x1 and x1 plus ix2 is your z, and you write it in that basis. So then it's sort of, the stress looks like some coefficient times dz squared, dz bar squared, and then something where you have mixed terms. And it turns out that the interesting guys are this guy and this one. And so that we call this one, in terms of the original stress, is certain complex combination of the stress tensor T11, T22, etc. And then the calculation which you do is the following. Solving the Beltrami equation. The T correlation function with this stress inserted is explicitly given in terms of just the correlations without the stress. Remember the bootstrap, there was something like that, okay? So that's exactly what is happening here. You have some sort of simple operator product expansion here. What are the coefficients? Well, conformal weights come, and there's a singularity when z goes to each of the points, square singularity. And then there are some first order singularities, okay? There's a term which depends on metric at the point, but if you take the metric, for instance, flat around the point, this is not there. So there's a very simple thing. This is called conformal word identity. The stress insertion gives rise to such identity. One thing to notice is that this is holomorphic function of the z. The z dependence is only here. It's an identity, okay? It's holomorphic z. If you take this t bar, this t z bar, that will be basically a complex conjugate kind of thing, and that will be anti-holomorphic function of z here. Okay, so it's holomorphic in the complement of these points. It has poles there. You can continue the calculation. You take two functions with disjoint subcompact supports away from each other and all the other points, and then you get that if you have two t's, then you get other interesting stuff. You get the stuff we had before, but you get also how the t's talk to each other. There's there's u minus v fourth power, and the second power, and the third power. That also comes from the calculation. And there's a number c, which comes, of course, because we started with this line anomaly here. So there's something which depends on c there. Okay, and now if you take more insertions, you can keep on doing that again. If you're interested, look at the paper with Joona. So basically, that's what you have. You have simple things which have poles at zi's, and when you have several t's or so it coincides. Well, now you can do the following now. Let's just proceed sort of we could do the defined sort of an operator now, call it Ln. So let me take a contour around one of these points, where I have the z. So I have one of these insertion points, and do a little contour around the point, and integrate the t. Take this correlation function, this correlation function, and do a contour integral around one of these points. So this z point goes around one of these points, but doesn't touch any of the points. Well, obviously you can do it explicitly, right? Everybody can do that because it's the z dependence is just these poles here. Okay, so but it's instructive to see what comes out of it. Okay. Well, first of all, so let's do it like that. So take the contour integral of t and multiply it by z minus zi to some power. Conventionally, I write it Ln, where the power is n plus 1 here. When this number is 2 or more, so n is 1, when this is 2 or more, you have a double pole at both here. So this holomorphic at zi if I multiply it by second power, so you obviously get 0. Okay? And if you multiply it by take n equal to 0, you get this delta, that was the single pole. And if you multiply it by something which is similar to zi, then you can deform your contour around the other points, okay? And plug it into this equation here. So obviously, there are around the other points, there are no poles here, so you're just integrating these guys here, and then you will get some differential operator like this acting on the correlation. It's a simple calculations, okay, coming from this formula. But it sort of gives a nice picture. It says that such an operator somehow annihilates your primary field when n is positive. The primary field is eigenfunction of this operation with conformal weight. And then you get something new when you take L minus 1, L minus 2, etc. And then one of the nice exercises in this business is to do the following calculation. Provided all I said to you is true, compute the commutator of two of these guys, Ln at zi and Lm at zi. Right? So you have two of these contours. And this is with, say, n, and this is with m. And you want to relate it to the thing where you have m and n. So you have to move. You have singularity when the points get together. It's fourth power singularity. And when the dust settles, you get this relation. What happens? You get this relation. This algebraic relation. So this algebra is called the Virasoro algebra. And it's a simple consequence of our two axioms. There's a similar story where you take the t z bar, exactly similar relations, and these two guys commute each other. Okay? So now you can do it many times. I can do it once, twice, 3 times, etc. And if I do it in some order, remember only negative guys were interesting. So let's take these negative guys. So take numbers which are k of them, k is arbitrary, and put them in some increasing order. And define the operation where I do this thing in that order. And the same thing with that. Then the following terminology. The fields where I act with that rule, these contour integrals. So now I have nested contour integrals around the point, first with some number nu1, then a bigger contour around that, another around that, etc. And I do that operation. It's obvious that I can, from this relation, since I know explicitly what the behavior here is, and the things which I didn't mention to you, maybe if I have more of these insertions, you can actually compute explicitly the correlation functions of all these fields. They are called the descendants of that field. And once the dust settles, is that just from this word identity, this correlation function is given by some differential operator acting on the points, a holomorphic differential operator and an anti-holomorphic. They don't talk to each other at all. One depends on the indices in the L bar and one on the other indices. And it's completely determined by the structure constants, by the C, the conformal anomaly, and this coefficients here. So this is how the local, the axioms give rise to this sort of local conformal invariance. Variations in the metric give rise to stress, and the stress correlation functions are explicitly determined. So that's a starting point to these operator product expansions, etc., what we were talking about in the beginning. I told you that there are these magic these primary fields, and then when you multiply them together, you get. So that's the starting point. And I did this to you because I want to do tomorrow a similar story in the case when you have this Kac-Moody symmetry. Okay, questions? Yes.
So the calculation of variation using these Beltrami equations, is it the same way as the physicists did? Because I think maybe they did it in a different.
Yeah, sure. Yeah. The only thing which, of course, crucial is there that your correlation functions have to be smooth functions in the complement of the point. Well, I don't think they didn't really do it exactly this way. I mean, but more or less. If you want really to prove it, you really have to solve the Beltrami equation and show that the solution series, there's a series solution and to prove it converges, etc. Okay. Now there's a choice. Either I still continue 5 minutes and do the Liouville theory, and then you are completely we have a reception now, right?
Yes, I think the reception is in there.
Yeah. So I'm not going to talk about Liouville, except now. You're the chairman. So, do 5 minutes.
I wasn't expecting to have to make a choice.
No, okay, let me not talk about it. Let's see. Yeah. I define the Gaussian free field, and I define the Gaussian multiplicative case. Well, let's just give it a break, and tomorrow I will start with the Wess-Zumino-Witten model, and in the end we need Liouville because we know we want to have a connection between the two, but at that point, then we can do this.